Welcome to Maths with EJD. In this video, I'll be talking about generating functions in cryptography and data structures. So it's a very important and interesting application of geometry, generating functions in this very important field. So in cryptography, in cryptography, of course, cryptography deals with, uh, concealing information so that, uh, unintended people do not get access, right? Like all this whole idea of encryption and the rest of it. So in cryptography and data structures, so I know this is really important in computing or computer science at large. In cryptography and data structures, generating functions, generating functions are essential for analyzing and optimizing the behavior of algorithms, particularly in situations involving probability, such as hash collisions or encryption reliability. So generating functions provide a structured way to understand and predict outcomes in these fields. So this is some kind of overview. Now let's move on to key concept here. Key concept. So generating functions can model a distribution of events, a distribution of events like hash collisions, like mentioned above, like hash collisions in data structures and and allow us to compute probabilities and design systems design systems for improved performance. Okay, now let's take an example which is about hash collisions. Hash collisions in a hash table. So a hash table M, a hash table with M slots is used to store N keys, to store N keys. Okay. Each key is independently hashed. Each key is independently hashed into one of the M slots with equal probability. Okay, so now we want to calculate the probability of at least one collision and explore how this probability changes as n increases relative to m. Okay, so that's our business. So let's look at the solution to that. By the way, don't forget, this is actually an example. Like I said, that's an example right there. So the solution, so step by step, the first thing we want to do is to model the problem, with a generating function. It's a generating function. Okay. So we say let x of xi represent the number of keys in the ith slot of the hash table. So since each key is independently assigned to any of the M slots. So we can say that xi follows a binomial distribution, so that we have P that X probability that X1 is equal to K will be equal to N combination K, then 1 over M raised to power K, into 1 minus 1 over M raised to power N minus K. So this is basically the binomial expansion thing. Okay, so we have that. We can then proceed to say that the generating function for the number of keys in a single slot is based on what we have up there now. G of x equals summation from k equals 0 to infinity of probability that x1 is equal to k x raised to power k. Okay. And that is basically the same thing as 1 minus 1 over m plus x raised to power m all raised to power n. Basically what we are doing is we are inserting all of this into this place so that after evaluating all that, now we have what we have here. So all of this now multiplied by x raised to power k, and that is what we have now. So we have 1 into 1 minus 1 over m plus x over m all raised to power n. If we do all of that, so this function, just like we know, a generating function actually encodes a sequence that of probabilities, so to speak. So this function encodes the probability distribution. So encodes the probability distribution, the probability distribution of the keys in any given slot. Okay. Now, the next thing we want to do is to, we have taken first step to model the problem with a generating function that has been successfully completed. So the next thing we like to do is to find the probability of a collision in a single slot. Okay. So to have no collision in a slot, there can be there can be at most one key in that slot, which is xi less than or equal to 1. There can be at most one key in that slot such that we have x1 less than or equal to 1. So the probability of no collision is probability no collision in slot, no collision in slot will simply be equal to probability that xi is equal to 0. We are talking about xi less than or equal to 1, right? So that means probability that xi is equal to 0 plus probability that xi is equal to 1. So less than or equal to 1, that's 0 and 1. Okay, so that's that probability right there. This is the probability that there is no collision. Okay, now that that is taken care of, then we can have from the generating function, right? So from the generating function, g of x, so we have that probability that xi is equal to 0. That means that k is 0, right? And that means we have g of 0 because you know xi equals 0. So that means x is 0, and that is equal to 1 minus 1 over m raised power n. So if you go back to the original expression, right? So this x is 0. So once x goes to 0 here, so that term is gone, and we have just you know just 1 minus 1 over m raised power n, and that goes. Then the probability that xi is equal to 1 will be equal to the coefficient, of x in g of x. That is the same thing as n multiplied by 1 over m multiplied by 1 minus 1 over m raised by n minus 1. So that's the coefficient of x. Because if you look at the whole expression, if you get x out of this place, so what is going to be left is all this big expression now. So find a way of taking x out, and this is exactly what you have. So you have n dot 1 over m dot 1 over 1 minus 1 over m raised by n minus 1. That's the coefficient of x in that place. So having settled that, so if we add these probabilities, adding these probabilities, so we see that probability no collision in a slot would be equal to 1 minus 1 over m raised to power n plus simply n over m into 1 minus 1 over m raised to power n minus 1. Okay, we have that. So because we also know that the probability of the next thing is the probability of a collision in a slot is probability collision in a slot that is equal to 1 minus probability no collision in a slot. That's a lengthy thing to do. So we can generalize this. That's the next step to take. Step 3. So step 2, yeah. Step 3 is to generalize for all slots. 3, generalize for all slots. Okay. So, and the way to do that is that the hash table has m slots, assuming the slots are independent. Assuming the slots are independent, the total probability of at least one collision in the hash table is probability at least one collision, and that is equal to 1 minus probability no collision in all slots. So then the probability of no collision in all slots can be computed using the multinomial distribution, but it can also be approximated using the birthday paradox. The birthday paradox principle for large n. So this is worthy of note. Birthday paradox. And what does that say actually? Simply states that probability at least one collision is approximately 1 minus e raised to power minus n squared all over 2m. So that is the approximation for that. So this is really important also, following from the birthday paradox principle. So, can we take an actual example? So suppose n is equal to 10 keys and m is equal to 23 slots. we want to compute probability that of at least one collision. Okay. So if we want to do that, we can use the approximation using the approximation formula. Using the approximation formula, so probability of at least one collision is approximately 1 minus e raised power minus what we just have now, n squared over 2m, n squared all over 2m, and that is equal to 1 minus e raised power minus 10 squared all over 2 times 23, because n is 10 and m is 23. So that is equal to 1 minus e raised power 100 all over 46. That is 1 minus e raised power minus 2.17. And that is 1 minus 0.113. Okay. And that is equal to 0.887, like that. So from that, we can infer that this means there is an 88.7% chance, 88.7% chance of at least one collision when 10 keys are hashed into 23 slots. And that goes. All right. Another thing we can do, we've done 3 steps so far. Another step we can take is to optimize hash table design. Okay. 4th step, optimize hash table design. So here now, to reduce the likelihood of collisions, we can increase the number of slots, M. For example, if M is equal to 50, instead of the 23 it was, I think. So for example, if M is equal to 50, the probability becomes P at least one collision, and that is approximately 1 minus e raised power minus 10 squared all over 2 into 50. So that is approximately 1 minus e raised power 100. This is 50. E raised power 100 over 100. So that is approximately 1 minus e raised power 1. Sorry, minus 1, right? Minus 1. So that is approximately 1 minus 0.368. And that reduces the probability significantly, sort of. So we have 0.632. At least it reduces the probability. So the more we increase the number of slots, the value of M, right, the better. So here we see that by doubling the number of slots, by doubling the number of slots, the probability of collision drops to 63.2%. Okay. So, I mean, from what we have seen now, impact of key to slot ratio, right? The likelihood of collisions increases significantly as n approaches m. So as n gets closer to m, we have the impact increasing significantly. Then applications of cryptography. This analysis is critical in cryptographic hash functions, where minimizing collisions ensures data integrity and security. Then, of course, optimization in data structures. Choosing the right hash table size is crucial for efficient storage and retrieval. So we see in all that generating functions provide a systematic way to model and solve such problems, making them invaluable for cryptography and data structure design. Yeah, thank you for being here so far. I can say somewhat that this is the last video on generating functions, except something else comes up. Of course, I still have one more video to go to complete the whole sequences and series thing. Of course, there are still other areas like using sequences and series to solve differential equations and everything, but I'll be treating those ones later. So, I mean, you don't want to miss out on anything on this channel already or anything that is coming. So because of that, you need to subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are. Comment, let me know if there's a problem to solve. Comment if you want me to teach a particular topic. And of course, in some cases where I have practice questions, be sure to put the answers in the comments. Then like and share so that more people can have access to these great videos. Till I come your way again, keep enjoying maths. Bye.